Good day, students. You are welcome to today's lecture video. Today we'll be discussing about determination of iodine number of lipids or fats. So let's first understand what iodine number is. What is iodine number? Iodine number is defined as the number of grams of iodine absorbed by 100 grams of lipid sample. So it's actually look at the actual number of the milligrams of iodine that is absorbed by a particular lipid sample. And if you talk about the significance of this iodine number, we can see that we are talking about lipids which we can have saturated lipid and unsaturated lipids in terms of the fatty acid composition. We can have saturated fatty acid and unsaturated fatty acid. So for unsaturated fatty acid, they have double bond. So if you are talking about addition reaction here, we are talking about iodine, which is a molecule that adds across each of the double bond of the unsaturated fatty acid. And the iodine number is actually give us the measure of degree of unsaturation of the fatty acid that is found in the lipid sample. So why do we use, now we see determination of iodine number, but in the experiment, bromine is used instead of iodine. So why do you think bromine is used instead of iodine? So the basis for the determination of iodine number is the addition of iodine across the double bonds of unsaturated fatty acids, but other halogens, halogen group 7 in the periodic table, they can be used to measure the degree of unsaturation. So if you look at the order of their reactivity, we can see that chlorine on top, chlorine, bromine, iodine, and astatine, right? So the order of reactivity is what? Is decreasing down the group, right? So if you look at the most highly reactive in the group 7 or halogen group is what? The fluorine, right? And followed by chlorine. Then which one? Followed by bromine, then iodine. So bromine is above iodine in terms of what? The reactivity. So bromine is more reactive than iodine. So in Damm's method, bromine is used in preference to iodine because bromine reacts more readily with unsaturated bonds than does iodine, as we highlighted earlier. So if we look at the reaction, here we are talking about the reagent is allowed to react with a known amount of fat that is in chloroform. A solution of fat is made in chloroform. This solution is actually 5 grams of your lipid sample is measured and dissolved in 150 50 mils of the chloroform. So this is the what lipid in chloroform solution that we are talking about. So your sample that you are going to use, you use what? 1 gram of the lipid was used to dissolve in 150 mils chloroform. So that is the solution of your lipid in chloroform that you are going to use for the experiment. So, and this solution is allowed, the reagent now, Damm's reagent is allowed to react with a known amount of the fats in chloroform, and the excess bromine can be actually determined. So if you look at this equation 1, we have unsaturated fatty acid reacting with bromine to give this addition product, okay, in equation 1. And the excess bromine can be determined by actually carrying out titration with potassium iodide, right? And you have this potassium bromide and iodine is liberated. And lastly, the product is now titrated with standard sodium thiosulfate in order to to estimate the liberated iodine that is actually as a result of what the reaction that takes place in equation 2, and you have equation 3 when you titrate the solution, the resulting solution with sodium thiosulfate. So the fat in chloroform is 1 gram of the fat dissolved in 150 mils of chloroform. So this is important. The fat solution that you are going to use for the titration, this is the concentration. So you can reduce the concentration here, and so for subsequent calculation, you should refer back to this 1 gram in 150 mils chloroform. So let's talk about the DAMS reagent. So we need to handle this reagent with care, because DAMS reagent contains bromine, pyridine, sulfuric acid, and glacial acetic acid. So you are told not to pipette, rather you use the burette setup that is in the film cupboard. The burette setup is not freely on the bench, it is inside the film cupboard. So you are not to pipette, you are to use that burette setup, because if you spill DAMS reagent on yourself, you can first wash it off with alcohol and then with plenty of water. So bottles of alcohol will be placed above the sink near the burette. So in case of any accident, so you can quickly, as a first aid, to actually do that. So, and all glassware used in this experiment must be clean and dry. So if you have a glassware that is wet, you have to rinse it with alcohol and allow to drain, and you are not to use the oven to dry the glassware. So in the first phase of the experiment, you are to carry out determination of the iodine equivalent of bromine that is in DAMS reagent. So here what you will do, you place exactly approximately 5 mils of chloroform in your conical flask, dry clean conical flask. Here is the titration. So if you are going to do it in duplicate, it means you have 2 clean and dry conical flags. If it is in triplicate, you have 3. So to each of those conical flags, you add 5 ml of chloroform, and then you add exactly 5 ml of your DAMS reagent into each of the flasks using the burette. Then you have to keep it in your locker for 5 to 10 minutes. This is an incubation period in order to allow the reaction to take place. Then after that, you add approximately 5 mils of 10% potassium iodide, and then you add 10 mils of water to each flask. Then you swirl it in order to mix the content. Then here you are going to, after that, you titrate the solution with standard sodium thiosulfate, and this titration is carried out with vigorous shaking to ensure that the 2 layers that are forming are mixing. Then when the mixture turns pale yellow, you are to continue the titration in dropwise until you have both phases they turn colorless. That is the end point of your titration. So you should take note of the number of mils of standard sodium thiosulfate you use in order to calculate the theta value. So here we have an example. We have this as our reading. We are using 2 conical flasks, so we are doing it in duplicate. We have the initial reading from our burette. We have first reading and we have second reading, because we have 2 conical flask. For the first conical flask, the initial 0, we started at 0, and we ended up at 11.50 mils. So we have volume of standard thiosulfate used as 11.5 mils. And for the second reading, which is our second conical flask, we started at 0, we top up our burette to 0, so that our calculation will be simpler and easier. So we have 0.00 as our initial, and our final will have 11.70. So our volume for standard thiosulfate use, we have 11.70. Now to calculate average theta value, we sum up the 2 volumes here, first reading, second reading, and we divide by 2, and we arrive at 11.60 mil. So this is the iodine equivalent in DAMS reagent. So in the second reaction, or in the second titration, we are going to carry out the dimination of the iodine equivalent of bromine that is not absorbed by the lipid sample here. So we have our we weigh our 5 mil portion of our lipid in lipid solution in chloroform. You remember the lipid solution we prepared by dissolving 1 gram of lipid in 150 mils chloroform. So that is the now solution we are going to pipette 5 mils, and we put in clean, dry conical flask. We are using 2 conical flasks because we are using we are carrying out the titration in duplicates. So we put that in our 2 conical flasks, and we are going to add exactly 5 mils of the DAMS reagent into each of the conical flasks using the burette. Then we transfer this flask to our locker for incubation period of 5 to 10 minutes. Then we titrate the standard sodium thiosulfate after that with vigorous shaking and making sure that the mixture turns pale yellow. When it happens, then we continue titration until dropwise until we have just 2 phases they turn or colorless. So also we have our readings here, initial, final, first and second reading. Our initial is always 0, 0. We make sure that our burette, we top it to make sure that it starts at 0, 0, so that we have a easier calculation. So now for the first reading, we have 17.5 mils of the standard sulfate used, and the second reading, we have 17.60. So now we take our average by dividing by summing the 2 volumes and divide by 2, and we have arrived at 17.30 mils. So now let's look at calculation. Now it's time to calculate. Now for the first question, it asks us to calculate the volume of standard thiosulfate equivalent to bromine that is absorbed by the lipid. So here what we'll do, our 2 average titer values, we subtract the first, look at it, this is our second titer value that contain our lipid sample, and this is our first titer value that is only chloroform. So we subtract this value that contain only chloroform from the value that has our lipid sample here. So we say 17.30 minus 11.60, and we arrive at 5.70. That is all for this question. And we go to the next question. It says calculate the number of milligram of iodine equivalent to bromine absorbed by the lipid sample. And we should remember that this is standard is given to us that 1 ml of 0.025 sodium thiosulfate is equivalent to 3.17 milligram of iodine. So we take this, we are going to use it for our calculation. Now, if we look at the solution, we are going to say that 1 ml of 0.025 molar is equivalent to 3.17 milligram. So this value now that we got 5.70 will be equals to X milligram. Now, X will now be giving us, as we cross multiply, we have 18.069 milligram. So this is the number of milligram of iodine equivalent to the bromine absorbed by the lipid. Now, we continue our calculation with question 3 that says calculate the number of grams of iodine equivalent absorbed by 100 grams of lipid. That is iodine number. You remember in the definition of iodine number? So this question is asking you to calculate that iodine number, which is the number of grams of iodine absorbed by 100 grams of lipid. Now, solution, we can see that 1 gram is equivalent to what? 1,000 milligram. So how many grams will be in 18.069 milligram? The value you calculated from the second question, milligram. How many grams will be equivalent to that in milligram that we just calculated from the second question? Now, X will now be equals to 0.018069 grams. So this is what we have. Now let's continue. You remember that 1 gram of your lipid is present in 150 mils of chloroform. You remember that? Then so how many milligrams will be present in 5 mil? You remember you pipetted 5 mil of lipid in chloroform, right? So how many grams will be in 5 mil? So we have what? 0.0333 grams. Okay, now when you continue now, you know that 0.018069 gram of iodine was absorbed by 0.033 grams of lipid. This is the value in grams of iodine that is absorbed, and the absorbed lipid solution is in 5 5 mils. So, and you are starting material, you started with 1 gram of the lipid in 150 mils. So this value that you calculate converted now of iodine was absorbed by 0.00333 grams of lipid. So how many grams will be absorbed by 100 grams of lipid? So now you cross multiply and you arrive at 54.26 grams. So this is your iodine number. This is what your iodine number. So what can you say now? The next question is says from your iodine number that you calculated, what can you say about your lipid sample? So from this iodine number that you just calculated, 54.26 gram, what can you say about your lipid sample? Now, possible explanation is that lipid sample contain relatively high amount of unsaturated fatty acid because there is what? You have a high iodine number. So that's bring us to the end of this lecture video. I can say thank you for listening, thank you for watching, and see you next.